Thevenin's theorem tells us that any two-port network comprising energy sources like this fixed voltage source here and a linear combination of resistors can be replaced by an equivalent circuit made up of a single voltage source with output voltage VTH, or the Thevenin voltage, and a single output resistance RTH. The value of VTH is given by the open circuit voltage across the outputs of our two-port network, and RTH is given by the ratio of the open circuit voltage to the short circuit current. That is the hypothetical current we would get if we were to short those two output terminals together. I say hypothetical, we almost never want to do that in practice. So in this example, let's see if we can find out what VTH and RTH should be. The first thing to realize is that the open circuit voltage is going to be determined by this 2.2 kilo ohm resistor and this 1 kilo ohm resistor, and of course our voltage source. And so the 5.6 kilo ohm resistor we have here is a bit of a red herring. It doesn't affect the open circuit voltage. Taking the 5.6 kilo ohm resistor away, all of a sudden this looks very much like a voltage divider circuit. So we have VOC is equal to 10 volts multiplied by R1, which is 2.2 kilo ohms, over R1 plus R2, 2.2 kilo ohms plus 1 kilo ohm. We can put that into a calculator or work it out ourselves. We find we have a shade under 7 volts is equal to our open circuit voltage, which is our Thevenin voltage. What value for RTH then? Well, for that we need to find the short circuit current. If we were to short from there to there, we would have a 10 volt potential difference traveling through a 1 kilo ohm resistor. So we would have 10 volts over 1 kilo ohm, which comes for our short circuit current. Our Thevenin then is going to be 6.875 volts over 10 milliamps, which will be about 687 and a half. Let's use what we know of Thevenin's theorem to find an equivalent circuit for the example that we have here. The first thing to note is that we can combine these two resistances here, and when we do, we can replace them with a resistance of 740 ohms. Now we've got a 6 volt battery, a 150 ohm resistor, and a 740 ohm resistor, and we can arrange them like this without actually changing our circuit at all. We can draw it like that. Hey, this looks very much like a voltage divider, with this voltage here being our open circuit voltage. So what is VOC? It is 6 volts multiplied by 740 ohms over 740 plus 150 ohms, which is 890 ohms. We'll crunch that number. It comes to 4.988 volts-ish. You know what? For me, that is close enough to 5 volts for our open circuit voltage. What is our short circuit current? Well, when we short our outputs together, these resistors no longer matter because no current will flow through them when it's got a better option to flow through a 0 ohm short circuit. So our ISC is going to be 6 volts divided by 150 ohms, which comes out to 0.04 amps or 40 milliamps. So now that we know VOC and ISC, we can find our Thevenin resistance. It's just the ratio of those two. So we're going to have 5 volts over 40 milliamps. That is going to be 125 ohms. So our equivalent circuit is going to look like this. We'll have a voltage source with a Thevenin voltage of about 5 volts. We will have a Thevenin resistance, RTH, which is going to be equal to 125 ohms. We will have one output terminal, we'll have a connection to ground, and we will have our second output terminal.